We're going to talk about our first lab and actually demo and kind of figure out what analysis we have to do for the first lab in this course. So we are going to be determining the total uncertainty in temperature measurements. So obviously we've talked a lot about temperature in our first kind of lecture. So why is temperature important? Well, we need to know how to control, measure temperature accurately, precisely, with high resolution in order to kind of drive or kind of control a lot of our materials processes and a myriad of other processes. So one example that I give here is when you're developing or when you're working with titanium sheet metal. I worked on this in industry when I was in Pittsburgh before coming to University Pacific. One of the critical steps is this process of annealing. So when you're annealing basically metal, you're basically kind of cooking the, essentially cooking the metal in an oven at a certain temperature for a certain time. And depending on your annealing process, so the time and temperature, you could change the grain size. As you increase the grain size, you increase the ductility, you drop the yield strength of your material. But additionally, in titanium, you could either create alpha titanium, beta titanium, or a combination of alpha and beta titanium. So these different structures will lead to vastly different mechanical properties. So if you're working on if you're annealing and you don't know the temperature plus or minus 10 degrees, you don't know what material you're making here, and that could have drastic, again, catastrophic, basically loss of life consequences when you're dealing with these materials. So we need to basically be able to control temperature correctly. You can kind of think of it in terms of like biology as well, where you need like bioreactors for cell cultures to grow different types of cells. If cells are at different temperatures, they could die or develop into new cells. Who knows? I'm not a biologist, but whatever happens with those cells. But again, temperature control is really, really critical here. So in this lab, this virtual lab, unfortunately, we are going to measure or actually analyze the data from 5 different systems. So we're going to measure the ice bath, so which should be at 0 C, room temperature, which should be at like around 25 C, excuse me there. Skin temperature, so the temperature of someone's skin, a cell incubator, and then a really hot system. So we're going to measure these 5 different systems with 3 different tools: a glass thermometer with integer temperature value markings, a Vernier Thermocouple, and a handmade T-Type Thermocouple. So we, unfortunately, again, in your lab report, you do not have to describe the materials and methods here. But if you're interested, and again, if you would actually want to do this lab, I would be happy to either go into lab and kind of demo it in person, or once we get back to kind of in person, I'd be happy to let you kind of run this experiment yourself and basically actually measure it by hand instead of just analyzing the data remotely. So we are going to get basically data files with 10 samples per second for 10 seconds. We are going to basically look at the data set and analyze it. So we need to analyze the temperature readings from the glass thermometer, the Vernier Thermocouple, and the handmade thermocouple. We don't have to make a schematic showing your VI. We then want to kind of analyze this data set. So are the data sets distinct statistically? So for each system, the ice bath, are we measuring essentially the same population? Do our error bars overlap for our 3 different measurements? And we want to do basically either hypothesis testing or look at our basically uncertainty, our error bars, in order to kind of analyze this. So that's basically what we're going to be doing in this lab in a nutshell. So first things first, let's look at the data that we have on hand. So first, actually, before we get to that, again, this is kind of just describing, again, what we're going to be doing in the lab. So the glass thermometer and Vernier Thermocouple, they're measured in C. So that data set, actually, let's open our data set. So I'm going to extract all. I want to extract it on the desktop. So let's look at our data set. So I have lots of these different data sets here. So glass refers to glass measurements, and 0 is obviously your ice bath, 25 is room temperature, skin temperature. This is your this is the temperature of the cell culture. Basically, this is the temperature of your where is it right here? Our cell incubator. And 80 is our hot system. So here are all the data files for glass. HT is for handmade thermocouple, and this is VT is your Vernier Thermocouple. And then there's this ice calibration and then a 100-degree centigrade calibration. We'll get to that in a second. So if we look at our Mathematica notebook, we're going to be measuring different temperatures, et cetera, et cetera. So the glass thermometer and Vernier thermocouple are measured in temperature in degrees C as a function of time. The handmade thermocouple is measured in voltage as a function of time. So the sampling rate was 10 samples per second. Glass thermometer has tick marks of intervals of 1 degree C. So when we think about uncertainty, we need to think about precision error and bias error. So the bias error is going to happen the same each time, and the bias error can be basically the resolution of your system. So if I have a glass thermometer with tick marks that are only in intervals of 1 degree C, what's the bias uncertainty in that measurement? Well, it's going to be plus or minus 1 degree C. So then you have to look up the uncertainty in the Vernier thermocouple. And then for a handmade thermocouple, the bias uncertainty in voltage is approximately 1 microvolt. So for the handmade thermocouple, we want to plot everything in terms of temperature, but we get values in terms of voltage. So we're going to have to perform a 2-point calibration from voltage measurements we obtained from an ice bath. So these calibrations are this ice bath, this ice cal, and cal 100. We measure the voltage in at a temperature that we know is, for the ice calibration, it's 0. For the calibration 100, it's 100 degrees centigrade with no uncertainty. Again, that's not realistic, but pretty much that's we're getting an estimate here. We're doing a calibration. So you're going to want to obtain an equation to calculate temperature from the voltage values and use that equation, to basically plot your results, or to obtain, obtain values in C. So we need to calculate the total uncertainty of temperature measurements for each tool and each temperature condition. Are they statistically distinct, et cetera, et cetera, et cetera. We know the drill at this point. So what we're going to do, not lecture 4, we are going to, let's start to kind of pull out some data and analyze it and see what it looks like. So let's just start out with glass of 0. So I'm going to copy, paste. I want to look at my data set first before I... So let's look at my dimensions. So dimensions, G0. So I have basically 5 columns of 100 measurements each, and you see here that this X value is in time, and 0 is your basically 0 is your temperature measurement. So let's pull out. Let's look at G01. It's always good, and you might want to include a I'm just going to do a list line plot. A list line plot of your. Actually, you do a list plot. We could do plot range, because we go from 0 to 10 seconds, and then we're going to eventually plot from 0 to basically 100. Will be our bound. So you can see here the data is pretty not too noisy. There's some fluctuations, again, measuring from 0, 1, et cetera, et cetera, et cetera. So that's a look of our data set. So we are measuring for G sub 0. So we're measuring that basically that ice bath 5 different times with 100 measurements. So what I would do, we know that the X values, so G sub 0, so let's look at all 1. Actually, let's look at 1. So if I grab all of the rows in the first column, I'm going to grab the time data. But again, I'm trying to measure, I want to measure the uncertainty in temperature. So time is not super important in this experiment. So this is all my temperature data in degrees centigrade. So if I want to figure out and plot, I need to calculate the mean values, and then I need to calculate our precision error as well, right? So I'm just going to calculate if I want the mean of this. I'm going to calculate that here. That's one mean value. I'm going to then repeat that, create a table function, do that for all my values from 1 to length of G0, G0. And so those are my mean values. So I could say that these are my 5 different means, 1, 2, 3, 4, 5. And then I could use my T-table test. So I know that if I have 5 means, actually that's why it's great. Good, great that I have this up here. So let's go back to our presentation. So if I wanted to do a 95% confidence interval, so 0.025. So if I have 5 means, so 2.776. And that's why I have that value here, times the standard deviation over basically the square root. Ooh, let's do this. Square root of the length. So here we go. So that would be my mean. This would be my, again, our precision error, which we've identified in lecture previously, right here. Precision error is going to be that T alpha over 2 nu S sub x over square root of n. And that's it. Let me fix this here. So this is my mean, this is my precision error, and I know this is my bias error, and I know my equation for total uncertainty is going to be my, so total uncertainty equals square root of G0P squared plus G bias squared. So for my first measurement, my total uncertainty is basically a value of 1. That's it. So I want to plot my mean, and my error bar is going to be this total uncertainty for that specific temperature or that temperature measurement, so like ice bath. So I could plot, basically what I'm going to try to basically eventually create is a plot on the x-axis, which you could kind of either label it as ice bath or kind of just say like this is like temperature of 0. On the y-axis, it'll be the measured temperature, and you want to plot basically your glass thermometer temperatures, you want to plot your Vernier Thermocouple temperatures, and you want to plot your handmade thermocouple temperatures. And you're going to do the same exact thing with the Vernier Thermocouple as well. So for the Vernier Thermocouple, again, all I do is just grab my data set, VT, Vernier Thermocouple here. I want to not pull up my email. I want to pull up my Mathematica notebook, copy it in, paste. There's my mean. There's my standard deviation. Excellent. And now I'm good to go. So all I have to do now, the bias, you'll look that up. Should know that. 0.4, who knows what that is. Anyways, you could just Google Vernier Thermocouple, and then basically you could kind of look at accuracy or uncertainty. We could kind of talk about that once you get to that part in your lab report. Now, one other, actually one critical data point is, like we said, so if I look at my handmade thermocouple measurements or values, so I'm going to look at import data. So you can see here, these values are in volts. So we need to kind of figure out, all right, what are we measuring here? What's the what's kind of going on with this data set? So let's see if I grab one. Thermocouple. So we are looking at this value right here. Oops, excuse me. Just pulling out my data set for the handmade thermocouple. Let's put this one right here. Actually, let's look at 25. So here, if I look at here, these are my values in volts. So now what I'm going to do here is start to analyzing and pull out that data. So I need to somehow convert volts here to temperature. So this is where the 2-point calibration comes into play. So I'm going to grab my ice calibration. So the ice cal. Look at this data set. And I'm going to just pull out value of 1. Actually, let's look at the dimensions of ice calibration. Yep, so we have 5 measurements as well. Let's flatten 1. Actually, let's not flatten. Let's keep that guy open. Sorry about that. So if I have my data set here, again, these are in values of volts, I can basically pull out some of the data set here. And I'm going to also do the same thing here for my voltage measurements for the 100 calibration step. So all I'm doing is I'm taking the mean, and then I'm basically transposing it as this kind of these 5 different, again, because we're going to plot, we know the temperature that this correlates to. So I'm taking each of these ice calibrations, so ice cal 1, I'm taking out all of my voltage measurements. So those are just the voltages. I'm going to calculate the mean of those voltages here. And then I want to, so this is the voltage that corresponds to my, basically a 0 degree centigrade temperature. Because again, we said that that ice bath had a temperature of 0 with no uncertainty. Again, very unrealistic, but that's what we're kind of assuming in here. So now that's just one measurement. I do this measurement 5 times. So I'm going to go and create this table from icecal, from 1 to length of icecal, and those are all my voltage measurements. So those are my data points. I'm going to transpose it with basically the temperature. So again, voltage, temperature, because again, I want to be able to basically work with this data set here. So we want to be able to plug in what is our voltage, because again, this is going to be our x-axis, this is going to be our y-axis. We want to be able to plug in voltage and get temperature. So we'll do the same thing for our 100 degree temperature measurement, except that doesn't work because I need to pull out right here, got 100. Here we go. And we go through right here. So again, this is the voltage now. See, the voltage is higher because again, I'm measuring a higher temperature. So you get a larger kind of, the larger, like when you look back at the Seebeck coefficient or the thermoelectric effect, you see that the gradient in voltage is proportional to the gradient in temperature. So larger temperature gradient from our ice bath to, you can kind of see that's why these values are almost 0, because the temperature gradient from our ice bath is effectively 0. But again, very small temperature fluctuations. But larger gradient in temperature, larger gradient in voltage, that's why everything's making sense so far in our world. So these are our data points. So I'm going to combine basically the ice bath calibration, the 100 calibration. I'm going to do list plot of my data. And you see they're all clustered here and here. So now all I have to do is a fit. So this is my data set. So if I want to fit models, I just want to fit my data to 1x. So let's look at my data set right there. And that is going to be my, possibly my function. So this will convert essentially my data set into, so let's name this our function. So let's see if this makes sense. Actually, let's go ahead and let's look at one more data set just to kind of make sure. So if I have HT room temperature, HT25. So I'm going to pull this. Actually, we have it right here. Sorry. So let's just do an example. So for room temperature, which should be around 25, I get this voltage. So let me plug in, because again, this function tells me the temperature at these voltages. Temperature on the y-axis, voltage on the x-axis. So if I do my function slash dot, x goes to here, this value. Let's see what my temperature is. It's pretty close. All right. Let's see, how about this guy right here. So kind of makes sense to me. Let's look at a higher temperature. Let's look at 80. Let's plug in here. Yeah, pretty much. I mean, again, some deviations to be expected, but yeah, not every, we're not going to hit that exact temperature. So you want to go through this data for the handmade thermocouple, find this function, prove it to yourself, and then you're going to use this expression to kind of calculate and convert your voltage measurements into your temperature measurements. So again, we need to see in this your lab report. I'd like to see some basically examples, nicer plots, obviously, of some raw temperature, basically for each kind of tool, and probably for each temperature. You can even do it on one single plot. You could kind of show the temperature versus time for some arbitrary temperatures, just some examples. Just again, you want to show your audience member how you calculate or how you obtain this data set. So some example curves of temperature versus time. You definitely you must show basically this calibration with the line and the fit, and describe how the fit. One quick question: can you measure this curve? Can we measure any temperature beyond 100 degrees or below 0? No, right? Because our 2-point calibration, our curve is only valid within these bounds that we've fit our curve. who knows what's happening beyond? It might not be linear, it might be exponential. So we can only we only know temperatures within these bounds of 0 and let's go 100 degrees C. But you want to show this fit, you want to show this equation, you could show your R squared value if you would like, but you need to include that. And then finally, the biggest your seminal graph in this report is going to be a graph of the temperature that you measure versus, you could do it as an error bar plot, you could do it as a bar chart. I could kind of show you if you want to do it in that method. Or on the x-axis, you could just do, again, for the ice bath, typically this will be like the 0 temperature, and the y-axis is the temperature you measure. So the temperature of your glass thermometer, temperature of your Vernier Thermocouple, the temperature of your handmade thermocouple. So these are the temperatures that you measure in the y-axis. On the x-axis, what the temperatures nominally should be, and then you're going to kind of, again, compare all those 3 different measurement tools. Are you measuring essentially the same bath? Are your error bars overlapping? What contributes most to your error? So look at this. We have a precision error and bias error here. What contributes most to your error? How can you improve this experiment? So these are all the things that are going to be expected in your analysis. So you really need to kind of produce these plots quickly, and then write really good basically statistical analysis of this experiment. So again, if there's kind of anomalous results, if there's kind of strange things that are going on, you need to kind of explain those well. So make sure you do that, and everything else is going to be just fine. So start your draft early, though, or show me basically a version of the draft ahead of time. That will really make your life a lot simpler. So make sure to do that, and you'll be fine. So good luck with that. Again, we'll be talking a lot more about it, but hopefully this kind of helps you get started on the data analysis. And if there's any questions, again, we have lab. We have quite a bit of time before this assignment's due, so get started on that early and you'll be ready to go. Thanks, and I'll see you all. Next lab will be a Helmholtz coil, and then we'll get into some really fun labs of basically doing Fourier transforms and then measuring strain as well. So get started on this early, follow the directions from kind of that technical writing guideline, produce some really nice, beautiful plots. Again, guide your reader, explain, walk them through this process. So you want to show them, this is the raw data. This is how you need to include the equations for how do you calculate mean, how do you calculate standard deviation, how do you calculate precision error, how do you understand bias error, how do you calculate total uncertainty. They all must be in your expression, in your equation. You need to motivate this study as well. So think about why temperature is important. Write an introduction with at least 2 or 3 chunks, multiple examples. We need citations here. Use Zotero. Explain this, and then you want to kind of describe your lab report in that context. So if I need, in my annealing of titanium, if I need a resolution of plus or minus 1 degree C, which tool can I use? Can I use my glass thermometer? Can I use a Vernier Thermocouple? Can I use a handmade thermocouple? If not, yes, no. If not, how can, again, I redesign looking at this and analyzing what contributes most to my total uncertainty? Where can I improve my apparatus? Those are all the things that must be discussed in this report. So again, look at each plot, analyze each data point. Are there outliers? So explain everything very thoroughly is my piece of advice. And again, show me a draft early, and I can kind of tell you where you need to kind of expand, where you can contract, and where you're doing excellent on. But again, everyone's going to do great on this. They're going to start super early, and there's going to be no issues at all. So yeah, that's about it. So I'll talk to you all next time. Thanks. Bye.